In the modern world of mathematics, it's not uncommon at all for mathematicians to work together and collaborate to solve problems. They're also not at all secretive. They will publish their work for others to see and have that work reviewed by their peers to check for accuracy and rigour. This was absolutely not the case in 16th century Italy, where this story takes place. At the time, to become an established mathematician, to get a job at a university or with the military or with nobility, you needed to make a name for yourself. You needed to be a known mathematician who was well considered by his peers. And at the time, the way to become an established mathematician, to get your name known, was to compete with other mathematicians in a duel of intellect. They didn't shoot each other with guns, although someone probably should have told that to Évariste Galois, but that's another story. The way that these duels worked, a mathematician would set another mathematician a series of problems and likewise would have problems set for them. And whoever solved the most problems, presumably in a certain amount of time, was considered the winner. And it was at this time that it became quite obvious that Niccolò Tartaglia had some deep insider knowledge in how to solve cubic equations. It was becoming pretty clear that he had a formula for solving cubic equations that no one else on the world had. And given all this secrecy, it's amazing that he agreed to allow the established mathematician Girolamo Cardano that solution. Now, the story goes that he didn't give it to him as is, he gave it to him in the form of a poem, and he only did it on the proviso that Cardano would not publish the results and let anyone else know what the solution was. At the time, Cardano was writing his book Ars Magna, which, among other things, was the first rigorous introduction to working with negative numbers. It might surprise you now that established mathematicians at that time, had such difficulty working with negative numbers when we teach it now in year 7. But they did. Cardano was the first to establish the rules of arithmetic for working with negative numbers, at least the rigorous numerical methods of working with negative numbers. In the book, he also introduced, of course, the cubic formula and the quartic formula. It was the first recorded demonstration of repeated roots in polynomials. And for our story, it also has the first recorded example of what we now know as complex numbers. Cardano introduced a simple little problem in chapter 37 of his book. He wanted to split an interval into two pieces where the sum was 10 and the product was 30 or 40. We're going to consider 40. Cardano solved this problem geometrically. He created a line segment of length 10, which we'll call AB. He created a point C on AB, which splits the line segment into two smaller line segments, AC and CB, and we'll say they have lengths X and Y. And remember, Cardano said in the problem that X plus Y should equal 10. That's why that length AB is 10 units. We can rearrange X plus Y equals 10 slightly and get Y equals 10 minus X. Now what we'll do is from that line segment AC, which has length X, we'll drop another line segment down to the point D and we'll say that length is Y. Now I've done this because the area of that rectangle now is the product XY. And thanks to our redefinition Y equals 10 minus X, we know that area is 10x minus X squared. Cardano now says, all right, let's subtract 40 from that area, which means that A minus 40 is equal to 10x minus X squared minus 40. Now remember, Cardano has said that we want the area to equal 40. So in other words, we can turn that into a quadratic. X squared minus 10x plus 40 equals 0. And when we plug that into the quadratic formula, as you can see, we end up with a negative underneath the square root. But if we just play around with it as if nothing was weird, then we're going to get two solutions. 5 plus the square root of negative 15 and 5 minus the square root of negative 15. And if you plug, say, 5 plus square root of negative 15 into our y equals 10 minus x, then you'll see that the other solution pops out for y. So in fact, those two solutions, they're x and y. And again, if we imagine that there's nothing weird happening with that square root, if we add x and y together, then those square roots are just going to cancel each other out because there's a positive square root of negative 15 and we're taking away the square root of negative 15. So they just cancel out. So we really do get 10. And if we multiply them together, that's just a difference of two squares, and we really do get the answer of 40. So it was a really interesting problem. It's demonstrating that with a really simple problem, we can end up with these weird negatives underneath square roots, but they kind of seem to work with our usual rules of arithmetic, which is quite interesting. And in the process of solving the problem, they just disappear and we end up with a normal number as we expected. We ended up with 40. So this was the first demonstration of what we now know as complex numbers. Cardano didn't quite seem to understand just what he discovered though, because on the very next page, he wrote that this is interesting but useless. So the rest of this topic is us demonstrating that these really aren't useless. They're amazing.